postdoc in Gran Sasso Science Institute, which is 1 hour away from Rome in Italy, in a beautiful place in the mountains of the center of Italy. And so his topic is mostly in gravitational waves and the formation of the prototypical, as you all know by now that gravitational waves have been detected and the prototypical sources are binary systems. So it will tell you about how these sources form. So please.
Good morning, everyone. Can you hear me well? So welcome to the Gravitational Wave Astrophysics course. I'm very happy to be here. I'm happy because I'm going to talk about gravitational wave astrophysics, which is what I do for a living, and I'm lucky enough also to like it. And we're going to talk about it for 4 days. But also, I'm glad to do that in Brazil. It's my first time in Brazil. I'm enjoying my time. I really like it. So thank you, Ricardo, for the invitation. And thank you to be here. So when I was thinking about this course, I came up with the idea to provide you a toolbox. So what I'm going to provide you is the basics to understand the field. So you'll have what you need to move your first steps in this fascinating field. So in the first lecture, we're going to talk about detectors and detection process, how we can actually gain information from data. So we will talk about data analysis, fascinating process. Second lectures will be about population analysis. So we do not have one gravitational wave detections. We have many of them. So we can learn from the entire population. And we learn about how we form these black holes and binary black holes in neutron stars that produces gravitational waves. Multi-messenger astrophysics is a powerful instrument. We are combining gravitational waves and traditional electromagnetic emission. It's going to provide us a lot of information about our universe. It's going to be like, we are going to merge together completely different scales. Scales on Schwarzschild scales, where you have gravitational wave emission, and galactic scales. It's a fascinating process. And then the Einstein telescope, which is like a future detector, a third-generation detector, that is going to provide us a complete picture of our universe with gravitational waves. And this is the right moment to talk about next generation of detectors, because we need the next generation of astrophysicists. I'm going to tell you about the challenges these detectors are going to face, and we need a new generation of astrophysicists that are able to embrace those challenges and provide solutions. So during lecture, we will see the basics, but we are going to see actual real research. During the hands-on sections, you will learn how to use 2 codes, GWFish and Cosmorate. GWFish is a code that allows you to do, like, in approximate way, but fast way, parameter estimation. And this is very important for next generation detectors. And Cosmorate, which is a code that provides you the redshift information of sources. Redshift is one parameter that you can measure with gravitational waves, and you need those kind of code to actually to model population with redshift. And these are actual codes that we use to do research. So this is real research. So you're going to learn, you're going to see, like, in details how these codes work. We will see instructions and exercises during the hands-on section. So in this lecture, we will focus on 3 things. Gravitational wave milestones. I mean, what we got so far with gravitational waves, like a brief history of this last 8 years, detection process, and parameter estimation of single events. Where you can find material in these slides, you can go to my personal webpage. I mean, the name of the page is quite easy, Brazil. So just to be like extra sure you don't get confused. You have the slide lectures. If you click on those buttons, I might update them during the days. So I mean, if you want to store them, just be sure to do that at the end of the school. And in the page, you also have the hands-on sections with instruction, but we're going to use those this afternoon. Okay, you might ask who I am. I mean, I was already introduced by Ricardo. So I'm Filippo. I'm a postdoctoral researcher at the Gran Sasso Science Institute. Here you see a lot of people. These are the people actually working on gravitational waves in Gran Sasso. Some of them are missing, unfortunately. We weren't, I mean, not everyone was there when we took the picture. What I want to say with this slide is that I mean, it's also I really appreciate their help to prepare these lectures because we are going to see like a broad spectrum of gravitational waves, and you could, you know, pinpoint like 1 or 2 people that actually are working on what I'm telling you in these lectures. So we are a big group doing a lot of research, and I just wanted to introduce them. You can contact me. I mean, as long as I'm here, you can talk to me, of course. But if I'm not here, you can contact me with my email address and ask question. Disclaimer. All of us come from different backgrounds. Something I might say might be like super trivial or super difficult. The only way to work around this is that we interact. So you can interrupt me whenever you want. Just raise your hand and we'll be happy to listen to you. So this is the only way we can fix this. Okay, so let's get into the actual lecture. I mean, the first thing I want to say is about detectors. Without detectors, gravitational waves would be like a pure theoretical science, which is good. We need theory, of course. But if we are here talking about gravitational waves in this super huge broad spectrum, is because we have detectors. So we have 4 functioning detectors around our globe. LIGO Hanford in the US, in the Washington state, LIGO Livingston in Louisiana, Virgo in Italy, close to Pisa, and Kagera in Japan. The 4 pictures you see below are like the pictures of detectors, and you can see that there is a common shape between detectors. Like a gravitational detector is a Michelson interferometer, and we're going to see that like in further details. When we observe gravitational waves, what we are doing is when we observe gravitational waves, we are in an observing run. So basically, we switch on the detector, we let it there, and we collect data. This is how it works. So far, we had 3 observing runs. What I'm showing here is the cumulative number of gravitational detection that we collected so far over time. And you see a nice thing, is that the cumulative number of detections is not linear, because at every observing run, what happens is that the sensitivity of the detector is improving. So at like even amount of time, you're collecting more detections. We are in an observing run, the 4th observing run. So here I'm showing you the 3 functioning detectors as function of time. So you can see like the amount of time the detectors were on, and you see a number like for example here you see 80 megaparsec. That is like the sensitivity of the detector, like the sensitivity of the detector of a typical neutron star merger, and you see that the sensitivity is improving over time. So the improvement of detectors are done when the detectors are switched off, of course. So we are exactly in the middle of the 4th observing run. We have like the O4A, O4B, like the first part and the second part. We are in the middle of the second part. And the nice thing is that in the second part, the 3 detectors are functioning. And this is going to be clear why we need 3 detectors functioning to do gravitational wave astrophysics, like at top. And we will have future observing runs with like current gravitational wave detectors, the O5 observing run. What I want to show here now is this. Yes, open it. Do I have internet? Yes. So this is GraceDB, which is the public database of gravitational waves. Everybody can access it. If you are part of the LIGO Virgo collaboration, you have extra information, but you can also access it. And I think you can also switch on notifications, so you can have like your phone ringing when a gravitational wave is detected. I mean, if you like, you can do that. So what I want to show here is this. First, this number here, 81 detection during O4A, so during the first part of the observing run. It means that in this observing run, we collected basically almost the total number of detection that were collected in the previous 3 observing runs. So I mean, the science is exploding. That's the message I want to convey. And then you have the list of detection. So you have, of course, you have like an ID, like the name of the detection, the source probability, if it is like a binary black holes, a neutron stars, or whatever. Other information, the GCN circular is like a formal circular that inform like a broad scientific community about the single detection, and the location where the actual detection is placed over the globe. And you can scroll down and see the detection that we collected so far during the observing run still ongoing. So this observing run will end in like next summer, basically. Sorry, next winter. I told you, first time in Brazil. Also, sun here is facing north. This, okay. It's a little. Okay, so detecting seasons, what we detect. I already told you something. So far we detected compact binary coalescences. So 2 compact objects merging with each other. We can have 2 black holes, so a binary black holes, a BBH. You're going to see like this acronym all over and over. So this is the best place to define them. 2 neutron stars merging with each other, binary neutron stars, and 1 black hole with a neutron star, a black hole neutron star binary. So what happens, you have like the 2 compact objects in the binary system. As time goes on, you have emission of gravitational waves, and then they finally merge. So this is what actually happens in a CBC, a compact binary coalescence. But we have other sources, of course, producing gravitational waves, so far undetected. For example, short duration bursts, like a burst of gravitational waves that can be emitted, for example, through supernova explosions. Continuous waves, so waves that are like basically fixed frequency, could be like wide binaries or neutron stars, as in the image I'm putting there, like a neutron star with an asymmetry, with a mountain basically, can produce gravitational waves. And the stochastic background that, like, in first approximation is whatever you do not detect. So this is undetected, but they also emit gravitational waves. Okay, so once you're done with an observing run, what you want to have is a catalog, like an official catalog of detection. And this is called the Gravitational Wave Transient Catalog. In the first one, they published the result of the first 2 observing runs, so you do not have like a one-to-one connection, but it's not a problem. So what you have here is, on the y-axis is the solar masses. So if you focus on the blue dots, these are binary black hole mergers. Basically you have 2 dots. These are like the black holes, the mass of the black holes right before the merger, and the dot on top. And the dot on top is the black hole mass of the remnant. The red dots and our black holes mass estimated through electromagnetic emission, so without gravitational waves, and the yellow dots are neutron star mass estimated with, again, electromagnetic emission without gravitational waves. Okay, so in the GWTC1, we have the first, of course, milestone, the first ever detected gravitational wave signal, which is called GW150914. The name of gravitational wave is, you have like year, month, day. So like it was 2015, September the 14th. And it's the one that I circled in yellow. And these are binary black holes mergers, so like a typical source that is measured with gravitational waves. And what I'm putting there is the actual gravitational wave signal that was firstly measured in 2015. The second milestone of this catalog is the first gravitational wave emission from a binary neutron star merger, GW170817, which was also the gravitational wave, like the first ever multi-messenger event, where we were able to get not only gravitational wave signal, but also GRB emission. And this is what I'm showing in the plot here. So on the top, you see the gravitational wave signal. You're going to understand like better this plot, but this is called spectrogram. You have frequency on the on the y-axis, time on the x-axis, and the color is normalized amplitude. And on the panels on top, instead you see the GRB emission that was measured by 3 different instruments. So multi-messenger astrophysics is a super powerful, sure.
This last one, GW170817, what you expected from the theory, that is the observational fact, but how massive you expected from the theory in this event?
What you expect?
This is the last massive you got it, right?
Yeah.
You expected exactly that from the theory or from the stellar evolution? That's the question.
Yeah, so this is a binary neutron star merge, so neutron star merging with each other. And neutron star masses can go from 1 solar masses to 3 solar masses. Like formation of neutron star from massive stars is like lecture 2. So we are going to see why we get exactly those. But the mass spectrum by neutron stars is very narrow. I mean, above 3 solar masses, you have black holes, so you are in the black holes regime. Just ask question. Multi-messenger, super powerful because it was like the definitive link between like a merger of a neutron star and short GRB. It was putative because before GW170817. We observed a kilonova. I'm going to tell you about kilonova in the third lecture. Binary neutron star mergers are a site of production of heavy elements. This is going to have an effect on metal enrichment of the universe. It was the first time gravitational wave was proved that they travel at the speed of light. This was foreseen by Einstein theory, but that was the first time gravitational waves were proved to travel at the speed of light. And we had an independent measure of the Hubble constant. So like just to say that with multi-messenger astrophysics, you can cover like a broad spectrum of the astrophysical world. Okay, this is instead the complete catalog that we have so far. We will have another GWTC probably 4 after the 4th observing run. This collects the second, so basically up to the 3rd observing run. And I think you can already say something about gravitational waves detections just by looking at this chart. Like a hint is that the events are ordered by distance. So the one on the left is the closest to Earth, and the one on the right is the farthest to Earth. Can you try to say something about this chart? Do you see a trend?
With small masses near of Earth, but far from the Earth, you just detect with big masses. So the amplitude of gravitational waves would be bigger.
The amplitude will be bigger.
Yeah.
Like a larger amplitude.
Yeah.
Okay.
I think so.
Yeah. That's a good catch. So yeah, basically, like the farthest events are the most massive one, but because do you think it's something like physical, or we are blind somehow, or we have like a selection?
Pyramids, I think.
There's also someone over there, but I think you can just.
It's a selection bias because we cannot see the smaller masses merge.
If they're too far away, we cannot see them.
Exactly.
Okay. Do you want to see something over there? No?
How long are we actually seeing Like, you say far from Earth. I mean, in terms of redshift, how far?
Yeah, thermal redshift is redshift 1, almost. Like the farthest one is redshift 0.8.
Okay, thank you.
So there's a selection bias. So if we want to see like object in distance, they must be massive. Otherwise, we cannot see them. Okay, but when we collect like a large number of detections, what we can do is population studies. So, and this is what we are going to see tomorrow. Okay, so that was like the, an introduction on the gravitational wave astrophysics. Yeah, sure. Sure.
Points? I mean, why do you have different points with the bar? Not the bar, but the arrow. Yeah, orange going to blue, and blue going to bigger blue.
Oh, yeah, I'm sorry. So, yeah, I didn't tell you. So orange dots are neutron stars. And somehow you can have like the two neutron star merges with each other, and they produce a black hole.
Ah, okay. So the orange is the neutron stars, and the blue is a black hole.
Yeah, for example, this
nice.
object, the very first object here is GW1700817, so the neutron star with a multi-messenger event. Then we have another neutron star, and you see that the final dot is half blue, half orange. This is because they sit in the so-called mass gap. So there are like two theories. Either you go from like neutron star, 3 solar masses, like 3.1 solar mass, you have a black hole, or black holes can be like larger than just 5 solar masses. So there is like an observation gap. We didn't observe black holes in the first mass gap, so that's why they put like half orange, half blue. But in this chart here, you have also black hole and neutron star merger. For example, this event here, neutron star. If you go above, you see black hole and the final black hole.
Okay, thank you.
Over there.
Is there as well a selection bias towards a near Earth for, because we don't see
Yeah,
so
because
heavy,
you would see
exactly.
like that's very interesting actually.
see
What we think is that
maybe the volume is not enough to contain such massive, statistically speaking.
yeah, basically so probably you already know, but like gravitational wave detector is observing like an entire volume.
Exactly.
So like massive black holes come from like massive stars. Massive stars are very rare, so you need like a big volume to actually have a statistic of massive stars. So that is another selection bias. Sure.
Yes.
These less massive events are so interesting for the school because you try to connect the exoplanets with black holes. I mean, events like that. So could you talk about the limitation to detect these less massive points? It's easier for all the diagram, or it's more easy to detect this one, like in the left, if you compare to this one in the right. You got it?
No, no, I think distance is the most striking effect in actually selecting because it is the amplitude, as it was said, goes as 1 over distance. So,
and how far you can go in the left?
Down, you mean low in masses? Can I chime in?
Sure.
No, the idea is that you remember the figures Filippo gave you a few slides earlier, those 150 megaparsec. That's the reach for binary neutron star. Of course, the mass is the gravitational charge. So the more massive the system, stronger the signal. So the reach scales roughly, I mean, it will give the demonstration in detail, but as a rule of thumb, you can say that the reach scales linearly with the mass of the source. So if for binary neutron star, which means 3 solar masses, it's 150, then you scale linearly with the mass. It's not mathematically exact, but as a rule of thumb, it scales linearly. So the problem is that up to 150 megaparsec, you tell me how many galaxies we have. I mean, the number of galaxies per megaparsec cube is 10 to the minus 2, I guess. Then you do the math, and you see that there is X number of galaxies up to that distance, and then you have to fold in the rate of such events. How many events you have per megaparsec cube or per galaxy of fusion. And the rate of fusion is, again, I mean, it will tell you much more about that.
Super uncertain.
The rule of thumb is 1 per megaparsec cube per mega year. That's the rule of thumb, per mega year per megaparsec cube. So unless you really look at few hundred megaparsec, you don't see anything. But for binding neutron star, that's exactly 100 megaparsec the reach you can have. So you see, we are not bound to have tens of binding neutron star with the present sensitivity. But wait till the end of the lecture, we will tell you more.
Can I ask a basic question about this plot? The horizontal axis, does it mean anything?
It's just, I mean, they are just ordered by distance, but it's not like, it's not on scale. No, it's not like, this is like a plot that we use to talk about the catalogs, but the horizontal axis is just, you know, like a counter. Okay, so let's go into the details of gravitational waves, like back of the envelope calculation, just to understand like the three main aspects that define you like a wave. So we frequency, amplitude, and polarization. So to understand frequency, in a Newtonian system, you can define like a dynamical frequencies as it is written there, and then you can do like this Frankenstein monster where you combine Newtonian physics and general relativity, and if you put like the Schwarzschild radio and on the place of r to the 3, we can get some numbers. So for example, if we take like a neutron star with a mass of 1.4 solar masses and a radius of 10 kilometers, you get a dynamical frequencies of 2 kilohertz. If you get a black hole, 10 solar mass in 30 kilometers, you get 1 kilohertz. So you see already that what is happening to dynamical frequency, if you have a supermassive black hole, has like the gigantic, enormous black hole that is sitting within our galaxies, you get a dynamical frequency of 2 millihertz. So this is to say that if you want to have your detector, and it is sensitive to a specific frequency band, you are going to see some events, not all of them, of course, because frequency is super important. Amplitude, to understand amplitude, we can look at the quadruple formula, the first one I put in the bullet points, or I think this is called also the Einstein quadruple formula, where you already see that the amplitude depends as 1 over r, and r is the distance. This is what I already said. And then you have that thing Qij, that is the quadruple moment, variation of the quadruple moment. So this formula here gives you the metric, like how space-time evolves through the passage of a gravitational wave, the full metric. But if we want to understand, we can define an estimator of the quadruple moment, which is dependent on the dynamical frequency. So, so amplitude is also connected with the frequency. We can do a bit of math, and if you're curious, you can go to the references and put in there, and you can get the gravitational wave amplitude of a binary system. So where m is the total mass of the binary system, r is the separation of the two compact objects, and r is, as I said, the distance. So you already see that the gravitational wave amplitude increases as you have like more massive systems, closer systems, and when they approach each other. So r, which is the distance between the two compact objects, as time goes on, is going to, the binary is going to shrink, so also the amplitude is going to increase. So this is like general rule of thumb to understand gravitational wave amplitude. Polarization, gravitational waves have two polarization, plus polarization and cross polarization. To understand the effect of polarization, we can look at this plot here, where we have a gravitational wave interacting with a ring of free falling particles. So the gravitational wave is traveling towards you on the zeta, in the zeta direction. It has frequencies of 2 pi over t. This is a very simple gravitational wave, and it's in the panel on top. So the plus polarization interacts on the perpendicular axis, y and x axis, and the cross polarization interact with the diagonals. When a gravitational wave passes through a free-falling particle, what happens is that you have a displacement, and the displacement is directly proportional to the amplitude of the gravitational wave and to the dimension of the free-falling particle. So just to give you like a back of the envelope numbers, if you have like a detector on Earth of 1 kilometer, and a displacement of 10 to the minus, so a displacement would be equal to 10 to the minus 18 meters. So it means that if you want to measure the passage of a gravitational wave, you need to measure like a displacement that is way smaller than the nucleus of an atom. 10 to the minus 15 is the nucleus of an atom. So if we put everything together, we can look at the amplitude of a binary neutron star system. We have 2 neutron stars of 1.4 solar masses separated at 19 kilometers at a distance of 15 megaparsec, which, if I'm not wrong, is the distance of the Virgo cluster. So you have an amplitude of 10 to the minus 21, and the like an initial frequencies of 10 hertz. This means that when the neutron stars start to approach each other, then the frequency is going to increase. Okay, so we can talk about the gravitational wave observation band when we look at different frequencies. So what I'm plotting here on the x-axis is the frequency. And then you have on top, like system, like astrophysical sources producing gravitational waves, and on the bottom panel you have detectors. So if you want to look at compact binary inspiler and mergers, you need terrestrial interferometers that are sensitive to these sources. And of course, if you want to look at more massive systems, so for example, merger of supermassive black holes, the dynamical frequencies decreases, so you need to go to space, for example, with a LISA interferometer. Okay, so now let's. I talked about gravitational waves. Let's see the detection process. So we have the gravitational waves passing through the detector. Here you have like a very simple schematic of how a gravitational wave detector is made. It is a Michaels interferometer. So basically you have a laser that is emitting, so like a laser source. The laser beam is splitted between the two arms, and at the end of the arms you have the mirrors that are going to reflect back the light, and a photodiode then is going to get the path of the signal, which is the one that you see over there. Of course, this is a fairly simplification because of gravitational wave interferometers are much more complicated. The mirrors must be isolated from actual ground motion, otherwise you wouldn't measure anything. I would like to show you a video if we have time. I mean, it's a 3-minute video that explains way better than me how a gravitational wave detector works.
This is not just a deck of cards.
Okay, do I have audio here? No? Ah, no, because this is a VGA. Where's the guy? Do you hear?
54 beautifully designed storyteller tactics.
In an interferometer, In an interferometer, a laser beam is split into two beams. Mirrors reflect the beams, so they meet again at a starting point. If now the distance to each mirror is exactly the same, no light will be seen by the detector. The waves of one beam extinguish those of the other beam. This is called interference. A passing gravitational wave distorts space, making one arm slightly shorter and the other arm a little longer. The light waves do not cancel each other anymore, and we now measure a tiny signal in the detector. Now we add an extra mirror in both beams. In this configuration, the beams bounce hundreds of times back and forth between two mirrors, before returning to the beam splitter. The intensity of the light in these so-called Fabry-Perot cavities increases substantially. The cavities boost the interference effect a few hundred times. The sensitivity is further increased with two additional mirrors, which recycle the outgoing light into the cavities, and with a so-called mode cleaner, which removes disturbing noise from the laser beam. The light power in the cavities is increased to hundreds of kilowatts. Even more complex optics and electronics are required in order to keep the mirrors properly aligned and in position. Ground vibrations at most about 100 nanometers are nevertheless millions of times greater than the vibration caused by a gravitational wave. Therefore, all components are mounted on horizontal and vertical vibration attenuators, the best in the world. While the ground is trembling, the mirrors and beams feel nothing of it, thanks to the super attenuators. Also, air presents a problem. It gives rise to unwanted vibrations, such as due to sound. Four so-called cryogenic traps provide an ultra-high vacuum quality. We can pick up hundreds of times more signal of a gravitational wave by extending the Fabry-Perot cavities to 3 kilometers. This and much more is needed to realize an interferometer for detection of gravitational waves.
I always, can you hear me? I always remain fascinated when I see how a detector works. It's an incredible instrument. Once you have your detector, you can actually get your signal. I mean, it doesn't look like that, of course. It looks like more this. So if you look in the middle of what you get from the Livingston interferometer, you can actually see by eye there is something there. This banana shaped, so you have like over time frequency is increasing, amplitude is increasing. So by eye you can see a signal. Most of the time is more, I would say, so sometimes if you're lucky it's like M4, most of the time is like Virgo. So yes, you have a signal, but you need a way to quantify that you have a signal. And this is called matched filtering. So basically what you want to do is to evaluate, to find the maximum SNR of your signal. So you have, just to explain this plot, you have like the actual signal coming from the detector. the gravitational wave, the weighted strain of the gravitational wave with the simulated signal, and on top you have the SNR. So, and you see that where you have the maximum of the frequency, you have also a peak of the SNR. So you want to do exactly that. But let's break down the, and what you're evaluating is that integral over frequency there, and I want now to look it carefully. So the first thing that you have in the integral is the denominator. That takes into account the detector noise. So where basically your detector is, how much your detector is sensitive to a given frequency. And usually it is represented with a PST, the power spectral density, where, and this is what I'm plotting here. You have frequency on the x-axis and the strain, or the PST on the y-axis, for the three functioning, for the three detectors functioning when you know, this is during the first observing run, GW 1504, 150913. And just a way to look to understand this plot. For example, you see that the Virgo, which is the purple line, the Virgo PST is higher than the Livingstone PST, so it means that Virgo is less sensitive. This is, but in today's hands-on section, you are also going to, by using GWFish, you are going also to compare PST with actual signal. This is going to be extra clearer. So basically, PSD is a measure of noise, so what is actually hampering you to get like a perfect detector and see everything. So noise is a fascinating word because it is what actually is not allowing us to see everything. So at high frequency, you have the photon shot noise. Basically, you are well in the quantum scale, given the distances that you're trying to measure with when you want to measure the gravitational wave passage. Mid-frequency, you have thermal noise. That can be, for example, the vacuum that is not perfect, the coating of the mirror that is not perfect. This is providing noise. And at a low frequency, you have Newtonian noise. This means like gravitational wave fields generated by, but not by the gravitational wave passage, but could be like anthropic noise or seismic noise, and this is going to have an effect on low frequencies. I'm putting down many references you want to look, you know, more into the noise part. In the matched filtering, then we need the signal, what is actually coming from the detector. Signal is made up by three components. So Gaussian noise, non-Gaussian noise, and the actual signal. So Gaussian, if you look at this spectrogram again, this is of GW170817 of LIGO Livingstone. You see the signal clearly, the banana shape. This is our neutron star merger. Like the whatever you see here, this is like the Gaussian noise, like random fluctuation around like a zero mean. And the thing that you see there, this is a glitch. So this is like a noise that is not predictable, that is not Gaussian. It's noise. So these are noise sources produced by the detector. So in this case, it was pretty clear that a glitch the glitch was removed. Sometimes the glitch cannot be removed, or it's very difficult to do that. Or probably even worse, you might have a gravitational wave signal that look like glitches. So this is the non-Gaussian part of the noise. Finally, in your integral, you need the simulated signal. We can do that because we pretty know general relativity, like at a fairly good point. So what I'm plotting on the left is a gravitational wave strain, so the amplitude over time. So you have on the left part the so-called inspiral chirp that is basically predicted by Keplerian orbit and the quadrupole formula that I showed you before. As you move close to the merger, you need numerical relativity to actually predict the strain of the gravitational wave. And then after the merger, you have a black hole, like a perturbation of a black hole that still is emitting gravitational wave that is called bring down. And then you have like a sitting black hole that is not emitting gravitational wave, like black hole, like a perfectly spherical black hole. So this is what happened, what you need to model when you want to do, when you need to model a waveform. And so what you have on the left is just for one system. What you do with matched filtering is compare the signal, like one signal, with like a data bank, the so-called template bank. And this is what I'm plotting on the right. You have the different masses, so the two component masses, mass 1, mass 2. Color-coded is different spin distributions. And all the dots are the template that were previously modeled through spiral chirp and numerical relativity that was used to, then is used to do matched filtering. And I don't know if you can see that, but you see like a little dot circle there. That is the gravitational wave signal that actually triggered the matched filtering for the first gravitational wave signal ever detected. So a gravitational wave is defined by many parameters. I just showed you like the two masses. A black hole waveform has in total 16 parameters. So 8 intrinsic parameters, which are the masses and the spins. So spins are vectors, so you have like 3 components per each spin. And 8 extrinsic parameters. It means like the source location in the sky, inclination angle, luminosity distance or redshift, or what you want to say, polarization angle, orbital phase, merger time, and eccentricity. This is just for a black hole. So with one gravitational wave signal, you get information on 16 parameters, sorry, which is fascinating in my opinion. With neutron stars, you have also tidal deformability parameters. So you have even more parameters actually defining your waveform. Just to give an idea, here I'm plotting 2 waveforms. Wind with aligned spins, so you have the spins aligned with the orbital angular momentum, so like only the zeta component of the spins. If you instead have like if your spin are instead tilted, so you have also a component on the perpendicular direction of the angular momentum, you have then a precessing orbital spin that is going to add a modularity to your waveform. So at a given parameter, you have waveform. That is what we can predict. But we want to estimate the parameters. We want to get so basically, we want to get information from data. We want to get information on the parameters. So what we want to do is evaluate a posterior probability distribution. So given like given data on gravitational coming from the detector, we want to estimate the parameters. What I'm plotting there is the primary mass distribution and the secondary mass distribution of the first gravitational wave signal. So the contours are basically highlighting the joint probability distribution of the 2 masses. And the dashed lines that you see on the plot, these are the marking the 90% credible interval. This is like a usual measure that is provided with gravitational waves. I mean, if your 90% credibility interval is very narrow, it means that you know a lot on that particular signal. Otherwise, you don't. So to run parameter estimation, you need what LIGO collaboration does is to run Bayesian analysis. So where you have the priors on the signals, do you have like an idea what a good prior choice could be? Usually. So, yeah, over there. Uniform priors, of course. So priors are takes in account whatever you know prior to actually having the data. So uniform priors are usually a good choice for example, for the masses. But for the luminosity distance, this is not a good choice because we know, for example, the universe is expanding, so we can have like, for example, a prior uniform income volume. So I mean, priors can actually take in account also a bit of physics. Then we have the likelihood, which is the most important part, on parameter estimation in this sense. So in the likelihood, basically, what you are what you're doing here, you're subtracting to the data coming from the detector, to the signal, the waveform at a given. So likelihood is data given waveform parameters. So basically, it is like you're assuming noise is distributed normally around around zero mean, and the operator, between parentheses, this operator here between parentheses is the same number that we were actually evaluating for the for match filtering. So these are likelihood. To evaluate the likelihood, you need to evaluate the so-called inner product, and this is exactly the same integral that we evaluated for match filtering. So unfortunately, posterior probability. So the posterior probability of given parameters has no analytical solution. So you cannot do math and try to get the posterior probability unless you're using very, very simple waveform models. So what we need to do is we need to sample from it. So for example, we can use MCMC or nested sampling, so which are like more modern way of sampling a posterior probability distribution, which takes a lot, unfortunately, because the likelihood takes a lot. You need to evaluate the waveform, you need to evaluate an integral over frequency, and it takes time, and you need to do that thousands of times, tens of thousands of times. But once you are done with parameters, just sure. The posterior, yes. But with nested sampling, of course, you also have an estimate of the evidence. Other questions? Just interrupting what, yeah.
Hi. So just out of curiosity, how long does it take to run one MCMC?
For like a usual, like a vanilla, days.
Yeah. Oh, okay.
Yeah, days. There are, if you want like the 15 parameters, you can do that like quickly, like on a matter of minutes. If you want just few parameters, so you marginalize over to the others. But days, that is going to be like a challenge for future gravitational detectors.
Thank you.
Other questions?
I have a question.
Okay, sorry.
So I guess before doing the parameter estimation, you also need to treat like the non-Gaussian part of the data before?
If you have like glitches, yeah, you can. Sometimes you can remove them, but it's an operation done by hand, basically. Yeah, it's a very lengthy procedure. The questions? Okay, once you have parameter estimation, you're not done because you need to deal with degeneracies. What is a degeneracy? The most famous one in gravitational wave is the one between distance and inclination angle, which is the one that I'm plotting here. So you can either have, so you basically see that these two parameters are like super correlated. And this is going to limit your predictivity on, for example, luminosity distance, which is like a super important parameter, as we are going to see over the classes. So I told you parameter estimation is very long to take, to perform, but we can approximate things and get like think faster. So this is like here I'm introducing today's hands-on section. You are going to learn how to use GWFISH. So basically what GWFISH does is an approximation of the likelihood. So if you compare this likelihood here to the one that I showed you before, this is like, we are approximating the likelihood as a multivariate Gaussian distribution, where the covariance matrix of the multivariate Gaussian distribution is that F matrix, Fij, that is called Fisher information matrix. You probably already have heard about it. Fisher information metrics are evaluated, again, using the inner product. The inner product is something that you already see all over the places in gravitational waves. But what you're putting in the inner product are partial derivative of the waveform. So what you're doing is fixing all the parameters of the waveform and partial derivative 1, for example, mass 1, mass 1, and mass 2, and you're building a Fisher matrix. GWFish does all that for you for free. So that's a good thing. So what you learned today, hopefully. So you learned about gravitational wave detections, how we detect gravitational waves starting from a detector. I told you about matched filtering and what takes in account noise of the detector, waveform models, and of course the signal. And then I talked to you very briefly about parameter estimation of one single event. Tomorrow, what we are going to do is population studies. So we are going to take in account to do like another different analysis, the analysis of the entire population of gravitational wave sources, and we are going to talk about astrophysical formation of gravitational wave sources. So we want to predict with our theoretical models what you actually observe with gravitational waves. So I want to acknowledge the contribution of people that helped me to prepare these lectures, and I'm also leaving you with further readings. Gravitational Waves Volume 1 and Volume 2 is like the Bible, probably, of gravitational waves. In Volume 1, you have all the derivatives of general relativity, detection, stuff like that. Volume 2, you have astrophysics, but don't spoiler. I'm going to talk about astrophysics tomorrow. And that's it on my side. See you this afternoon. I think we have time for a couple of questions if you want.
Plenty. So while you think about,
you showed how the experiment is made, right? With all the apparatus to not having any kind of interference from the ground vibrations, but it's not perfect, right? I mean, how is the background due to the Earth, and how it comes through the detector, and it comes from, I mean, earthquake or stuff like that? I mean, what kind of noise do you have?
Yeah, so this is like on the Newtonian noise part. What comes from vibration from Earth, that could be like earthquakes, seismic vibration, or also anthropic vibration. And in the PSD, this amperes the low frequency part. But it's like low frequency, like below 10 hertz. But then you have like a limit that it is not possible to, so like current gravitational detectors are limited at 10 hertz. Future gravitational detector like the Einstein telescope, as I'm going to show you, can go down as 1 hertz. But you can do better than that. If you want to go down 1 hertz and to see like all the other sources, for example, supermassive black holes that have like super short frequency, you need to go space. Because on Earth, you are always limited by this 1 hertz disturbance, noise disturbance, which is given by the ocean. Yeah, this is related with ocean waves on Earth that is going to provide you this one. And it's fascinating how noise works. Is super fascinating. Like down 1 hertz, you need to go space.
Okay, great. Thank you.
I realized that in my geographical poll, I have not been inclusive. Is there anybody from outside Latin America? No.
Well,
okay, too bad. The coffee break is not ready yet, so you better ask questions.
When you say the nice priors you have are uniform, that's a prior, right? I mean, why is this? What kind of parameters are they? I mean, this is a choice in itself, right? Sometimes a uniform prior is like the non-informative ones. Sometimes they are more appropriate, but sometimes they just they are overweighting some regions which are unexpected. I mean, this is, what is your take in this? I mean, which parameters are you talking about? Some parameters that we know absolutely nothing about, or parameters that we kind of know something about from other areas, but we don't really have information? So that's my question there.
Yeah, the prior choice is like a huge topic. Usually they choose like flat priors to be uninformative. You can do also population-informed priors. For example, tomorrow I'm going to show you how we get information from the populations, and then you can say if this new detection is coming from the same population, why I cannot use those priors on the population on that one. There are analyses done like that. What I think people do in gravitational wave is that they take in account different priors. Time to time, you have like new papers saying, okay, if we change this prior, we get this posterior, and it's changing our conclusion, or it's not changing our conclusion. But you need to keep in account priors. Sure. Question over there? I think, do you want to make a question?
It's not a question, I mean, it's a comment, by the way. So first of all, I would like to know how much students are from the undergraduation. Could you give me a point? Okay, so most of them. So the comment is about the Michelson. The Michelson-Morley experiment it's from 1887, so it's very old. Could you connect this experiment with the first one from Michelson-Morley?
Ah, yeah, sure. Thanks for the question. So yeah, the Michelson interferometer is not something new. I completely forgot to say that about. It comes from the last century. If you might have seen it during your physics lab, probably. You usually do that for measuring the refraction index of materials. You might probably have seen that. Yeah, so like the history of gravitational detection is fascinating. They started like in the 70s with like resonance bars, like huge cylinder of like one pure material to catch like high frequency gravitational waves. But then people realized that the Michelson interferometer was more suitable because it can allow you to go to the lower part of lower frequencies where you have compact object mergers. So that's why the Michelson interferometers actually made a huge leap in this field. If you want to measure gravitational wave, you need the super attenuators. So the vibration isolant with otherwise it would be like a microphone or seismometer or something like that if the mirror would stick on the ground. But yeah, the general idea is not new. That's also very fascinating.
Could you please back to the graph with the frequency where we have the noise? Yeah, the noises. Yeah. Where do we expect to find the signals of binary systems? In
this frequency?
Which frequency?
You're going to see that this afternoon.
Where? In which frequency?
So for example, I mean, if you go back, let me go back to this. Okay, the frequency, this is like a binary neutron star merger. So the frequency starts at 100 hertz. So basically, if you go back here, you would have like at 100 hertz, like this, I mean, you could potentially see also below 100 hertz because below 100 hertz, like the binary is just, the two neutron stars are just farther apart. But like you would see at 100 hertz, then you would see the sig. But this is going to be like super clear in this afternoon hands-on section. What you're going to do is to plot the signal over this plot. Basically, but this is going to be extra clear. What the match filtering thing is measuring the area between the signal and the bottom part of the PST. That area is the signal to noise ratio.
So the Newtonian noises kind of don't affect the signals in the most part of the time because they are lower frequencies, or not?
In the case of the BNS, which is merging at higher frequency, you're safe in a way. But what happens is that the frequency depends on the masses. So if we want to, what's the point? So if you want to measure like objects that are more distant, you need to go to lower frequencies because more distant means also higher masses, because what the detector measures is the detector frame mass, which is the mass times 1 plus z. Z is the redshift. So if you go to higher redshift, more distant, you are going to have like higher masses, so you're going down in the frequency spectrum. At that point, Newtonian noise is your worst enemy. But for BNS, we are safe.
Okay, thank you.
If I can chime in. So remember the relationship between the mass and the frequency that he gave earlier, that's for the maximum frequency. But of course, the system can have an arbitrarily large separation. So the wider the separation, the lower the frequency. So from the max frequency down, you have all frequencies. But of course, you don't see them because then you have a lot of noise that makes you blind to low frequency. So you just see the last part, and because all the previous part is lost into noise.
So if you're going to go to lower masses and to higher masses and higher redshifts, how are the future observatories planning to actually lower this Newtonian noise? I mean, what is it? What's the trick there? Because so it's not photon count, so it's not a question of luminosity. Thermo, it's already down. I mean, I guess you have to cool down some parts of the experiment. But then the Newtonian noise is really critical. So what exactly is that, how the new experiments are going to be done?
You go underground. That's your solution. If you go underground, you can kill a lot of seismic noise. I mean, you need to build your detector in a quiet place, of course. But the solution is to go underground. But even if you go underground, you have the 1 Earth's wall that is going to kill you, and you can't do much.
Doesn't matter how far you are from the ocean.
It matters. It matters. If you are like. Now, I don't know these details, actually, but it matters. It matters, yes.
Are you going to talk about the expansion of the universe and the interference in the gravitational waves?
Yeah, no, what I was saying is that on the priors again,
it's kind of a usual redshift or not?
What do you mean, sorry?
Because we have the gravitational waves and the universe is expanding, so we have interference in the frequency or not with the expansion of the universe.
Oh, I see what you mean.
The emitted frequency is not the same as the received one.
Yeah. You change because of the expansion of the universe, but is it the usual redshift or not? Yeah, it's the usual redshift.
So gravitational waves are. I am going to tell you about this. Third lecture, gravitational waves are standard sirens. It means that when you measure them, you measure the luminosity distance because of the 1 over r, 1 over dl. So when you measure gravitational wave, you are measuring also the luminosity distance of the source emitting the gravitational waves in an independent way. And it is something super precious. Then if you want to connect the luminosity distance with redshift, you need, of course, to fix cosmology. Because the gravitational wave is the integral over, the Hubble parameter. But you can avoid that if you see the host galaxy. So if you have luminosity distance from gravitational wave and redshift from other sources, like the host galaxies, for example, then you can combine them and then yes. Yes, you're going. If you're patient, we are going to see that. Yes, on the recession velocity. Sure.
Last question.
Yes. How do we differentiate if the gravitational wave signal came from neutron stars or black holes or another events?
Yeah, thank you for the question. So basically, what you can measure with a gravitational wave are the best option would be to measure tidal deformability. So it means that when the two neutron stars are approaching to each other, they start to deform because of the gravitational wave interaction with each other. Black holes do not do that, of course. Neutron stars do that. Tidal deformability is a parameter that is given by the waveform. However, recurrent detectors is very difficult to measure it or to put constraints. So your solution go back to the masses. So if the measured masses are below 3 solar masses, you can be sure that you are dealing with a neutron star because the limit. So it is predictable, the limit between neutron star and black holes, given the equation of state of neutron star. If you assume that, you put a limit, and then you can say safely that okay, this is a neutron star. But of course, with gravitational waves, potentially we can also measure the equation of state of neutron stars, and this is a very fascinating work.
Of course, if you have the prejudice that all these compact objects come from the collapse of a star.
This is going to be clear tomorrow. Just be patient.
Okay.
One brick at a time.
Let's thank Filippo again.
Thank you.